transition probability, right? As long as we have transition matrix, then we can calculate conditional probability for any time difference using matrix notation, right? Okay. So now we are going to talk about distribution or probability for a certain time, not conditional probability. Okay. So I skipped some information last class, so let's try to understand step by step. First one, for your convenience, we are going to assume that this state space includes finite number of states, okay, finite number of states, let's say k, and we can index 1, 2, up to k for each state, okay, for your convenience. Now, to understand initial distribution or stationary distribution and so on, okay, we are going to consider finite sample case, okay, and these states are indexed by 1 to k integer numbers, okay. And then second step, okay, so when we consider x of n, this is a random variable representing state of the system, right? And then based on the definition of state space, this random variable can take any number from 1 to k, okay? And we know that this distribution regarding this random variable might be a discrete or continuous distribution, discrete, right? So as long as we know PMF, probability mass function, or probability assigning for a certain state, then we can calculate the probability, right? So let's say we are going to consider such a distribution as a vector, okay? First component, probability that xn equals 1, the first state. Okay, second element, probability that xn equals 2, up to probability that xn equals k. This vector includes all the information about probability mass function for xn, right? Under this situation. Okay? Okay? And we are going to use different notation. Okay? For xn, this vector is denoted by vector a sub n. Okay? Actually, if xn is a discrete time Markov chain, then this an changes as n increases. Okay, I'm going to show you an example later. Anyway, this one changes as time goes on. Okay, and so far we discussed about conditional probability. Let's say xn plus k equals j, given that xn equals I. We can calculate this using Chapman-Kolmogorov equation or matrix operations, right? Okay, and then the question is how to calculate this one. A certain time, a certain point of time, and how to calculate this distribution of xn. That's the question. Even though we know this conditional probability for any k, time difference k, we also need to know this distribution, probability that xn equals I. Otherwise, we cannot calculate a probability that xn plus k equals j, right? So we need to know such information. Okay. So the origin of this probability might be from x0, right? Right? the first state, okay, initial. And then as long as we know this conditional probability, then for any n we can calculate a n, right? So this a0, let's say this one is actually probability mass function for x0, right? Probability that x0 equals 1, 2. Probability that x0 equals k-dimensional vector. Okay. As long as we know this a0, we call this initial distribution of the chain, Markov chain. Okay. And we know this transition probability. In other words, transition matrix. Then we can calculate this distribution for any n. Right? How? If we know for a certain DTMC, let's say xn, n is from 0 to infinite. Okay. If we already know transition matrix regarding this chain and initial distribution of this chain, then this an can be rewritten by a0 times p to the nth power for any n. Okay. So why don't you think about a1, just first case? Okay. First case, say this a1 represent first component probability that x1 equals 1, 2, probability that x1 equals k. Okay, and based on this equation, this one is probability that x0 equals 1, 2, probability that x0 equals k times p002, p0k, pkk, pk0, this matrix, right? Okay, and then let's think about this one first. Okay, x probability that xn equals 1 might be the same as summation for all I in S times probability that x1, right? x1 equals 1 given that x0 equals I times probability that x0 equals I, right? Based on the definition of conditional probability. Okay? Okay? And then this part is corresponding to all the elements in the first vector, row vector. Okay? And then 1, 2, 1k, k1, 2, kk, right? Right? And then this conditional probability is corresponding to all the elements in the values in the first column of the matrix, transition matrix. Okay? So now the first element of A1 is the same as this vector, row vector times the column vector, first column vector in the transition matrix. Okay? And then we can calculate all the probabilities with the same structure. I mean, matrix operation, right? What if we consider A2? Then we can multiply this matrix again by A1. A1 dot matrix P, then we can get A2, right? So I mean, A2 is A1 times P, and A1 is the same as A0 times P times P. So A0 times P squared. Then we can get distribution, probably mass function for x2, okay, and so on. So as long as we know initial distribution and the transition probability, then we, for any n, we can calculate the distribution of xn. Okay, that's the concept in this slide. About how to determine whether this distribution exists or not, and unique or not. Okay. Anyway, other than initial distribution, we have another distribution, very important distribution called stationary distribution. Okay. If we have a discrete time Markov chain, then we can construct transition matrix, right? Transition matrix. And we are going, for your convenience, we are going to use the same structure. Let's say finite states, and each state is indexed by 1 to k. Okay. Okay. Then let's think about this equation, two equations. So pi represents row vector with k elements, a certain vector, okay? Pi represents a certain vector including k elements, and then this pi is satisfied with this equation, pi times p equals pi, and then sum of all the elements in pi equals 1. Two conditions. As long as pi satisfies these two conditions, then pi is called stationary distribution. Of chain A DTMC Xn, if Xn is defined on S. Okay, that's the definition of stationary distribution. Okay, and then how to interpret this? Well, we have two different ways. First one, stationary distribution. So any component of this pi represent long run fraction of time that this chain stays in the certain state. Okay, pi I represent. So if we run this system long time, let's say 2 years. Okay, then what is the fraction of time that the system stays a certain, let's say I, state I, during 2 years? Okay, then this fraction of time represent pi i's element of the pi, if pi is the stationary distribution of the chain. Okay, or if we operate the system long time after 2 years, what is the probability that this state of the system equals a certain state, let's say I? Okay, if this stationary distribution is unique for a certain chain DTMC, then this probability is the same as the pi I. Okay, but surprisingly, as long as we can calculate this, solve this system of linear equation, then we can get it. We don't have to use Markov chain, MATLAB, matrix operation again and again. We don't have to do it. Okay? As long as you can solve this system of linear equation, then you can find it. Okay? And one more question. How many, in this system of linear equation, how many unknown variables in the system of linear equation? How many? K, pi 1 to pi k. K unknowns. But how many equations do we have? Linear equations. Here, how many? K number of linear equations we have in this formula. And then this one more. So we have K plus 1 number of linear equations. What happened? What happened? We can come up with 3 different cases. First one, no solution. Second one, infinitely many solutions. Third one, unique solution. So if we have unique solution, okay, one of the equation might be dependent of other equations. Okay? Do you know what I'm saying? So I'm going to talk about how to calculate this pi right after I explain how to use it. Okay? Okay. So for a certain DTMC, let's say we are going to talk about how to determine whether unique stationary distribution exists or not later. Next slide, next week. Okay? But assume that we already know that this chain has the unique stationary distribution and denoted by pi. Okay? Then we can calculate long run average value limit. If time goes to infinity, then function of the state of the chain, summation of the function of the state of the chain divided by time n. Okay? Then this value is called long run average value, like long run average profit, cost, something like that. If in the SS inventory policy problem, okay, this profit function is depend on as a function of the number of items at the end of each day. Okay, then we can calculate long run average profit using this formula. Okay, but as long as we can figure out the stationary distribution of the chain and it is unique, then this one is the same as this for all state I, function of I times pi I. Okay? That's the main result of this structure.